Welcome to the Orion meeting. I'm David Fields, filling in for our president, Don Spong, who is traveling and doing great things in physics. So I'm going to go ahead and tell you a little bit about our speaker tonight. Peter Thornton is here, getting everything set up. Congratulations to him for being flexible. He's a distinguished scientist and section head for Earth System Sciences at Orion. He studies the biogeochemistry of land, coastal, and aquatic ecosystems, and incorporates that knowledge into computer models to improve predictions of future climate. He's a mentor to several technology within the Oak Ridge Public Schools, and he serves as a board member for the Oak Ridge Public Schools Education Foundation. So he wears many hats, successful with those hats. One of the recent successes was the RAMSAT project. It's a CubeSat that was built in Oak Ridge with a lot of mentoring and a lot of cooperation from Oak Ridge and other local groups or other groups. So I take great pleasure in turning this over to our speaker. Thank you, Peter, and thanks to all of you for being here.
All right. Full screen on it. So thanks a lot for the invitation to join you, and we've gone to great lengths to find a spot here. So we'll dive right in and not take any more time. As David mentioned, this is a middle school technology project that was begun by the classroom teachers in the STEM program at Robertsville Middle School, and that's Todd Livesey and later on Eli Manning both had this vision to bring a very sophisticated technology project into the middle school classroom. So I'm going to give you a little bit of the history of how that came about, and then I'm going to talk to you about some of what we ended up doing as a team of educators and mentors and students, and a much broader community than that as well. Yeah, so I'll talk about the results of what we've done and some lessons learned from that, and take any questions that you have. So we're going to start with a brief history of RAMSAT. The project went for about 7 years. So we started in 2015. That was before I joined it. It was an enrichment class at the middle school, and Todd Livesey was, as the STEM teacher there at that time, was given the opportunity to form a class, and he had an existing collaboration with NASA through the Project Lead the Way program, and was in touch with his people at NASA, and they came up with some ideas about maybe exploring the use of small satellites as a topic that the middle school kids might get interested in. And they spent a year going back and forth to with their people at Marshall Space Flight Center, and came up with some ideas eventually that the Space Flight Center said, yeah, we'd actually like you to put in a proposal to try to build a satellite around these ideas. And so the students began working on designing their science mission in 2016. And that's about the time that I came on board with a number of other mentors, some people from Oak Ridge National Lab, people from the community at large, people from NOAA, and including David as one of our panel of experts to give us guidance. We developed a proposal and submitted that to NASA in 2017. They have a CubeSat Launch Initiative program, and that program allows mainly universities groups, but also a few high school groups, and never before a middle school group, to have the opportunity to launch a satellite, CubeSat. And so NASA, if you win this competition, NASA pays for the launch, but then the group has to develop get the funds to actually build the the satellite itself and whatever ground support systems are required. And NASA pays for the launch integration into a launch vehicle and deployment into orbit. So with that promise in mind, we submitted our proposal, and we were in fact selected for the mission in 2018. Got that news from NASA. And then it all became very real about having to raise the funds to build a satellite and then develop within our team the understanding of what it even meant to build a satellite. And so we got real busy doing that and working with the students every step of the way. And I'll tell you more about the mission and the design as we go through. This is just to give you an overall sense of the timeline. Finalized the design and completed the initial purchasing in 2019 for the components. You may recall a global pandemic arrived, and so we got delayed in the same way that the whole rest of the world got delayed, but we actually managed to push through that. And working via Zoom and remote sessions with the students, and some very nice accommodations from the school district to get together with a very small number of students in very well-controlled circumstances to be able to do some of the building of the hardware. We were actually able to get the software designed and a first full build done in 2020. We ran into some hardware issues that required an unbuild of the satellite and then a full rebuild. And we got that done in 2021 in time for a launch opportunity in June. So in June of 2021, we launched on a SpaceX Falcon 9 rocket as part of a resupply mission to the International Space Station. And there went into storage for a couple of weeks before the RAMSAT itself, our small satellite, was deployed into its own orbit and began operation immediately thereafter. And the mission operated successfully from June of 2021 through October of 2022. So we had a 16-month window of operations. And I'm going to show you some of the results of that successful mission. The satellite deorbited in October of 2022, somewhere over the southern Indian Ocean. It got too close to the atmosphere and burnt up, which was what we knew from day one was going to happen. We actually got more time out of the mission than we thought we might. Our estimates were 9 to 18 months, and we got into the outside edge of that at 16 months of operation. So just to give you a bit of a sense of what we were doing and why, this was not about, can we get a satellite into orbit? It was mainly about, can we connect with as many students as possible with a really exciting set of technology and have them engaged from the ground up in doing something exciting and life-changing for them. And we think we were successful with that. We did end up engaging over 200 students over the 8 years of the program. And that consisted of classroom experiences for grades 6 through 8. And of course, the students over that time period are rotating through the middle school classrooms. And then a lot of those students going on to the high school, and a few classes even over this period of time going on to their early years of college. And we had both the classroom experiences in the middle school and then peer mentoring, meaning that the high school age students were coming back and helping us as mentors and instructors in the classroom work with the students and pass on what they'd been learning. So very cool engagement across multiple age groups with the students that way. So to go back then to what the mission was, you remember in November 2016, the Gatlinburg wildfires, biggest and most devastating set of wildfires in this area for a long time. And So this was on the minds of the students as they were being prompted to come up with some ideas for what a satellite mission might look like. And a few of them had the idea that they could put a camera in space and try to observe the regrowth of the forests in that Gatlinburg area following these massive wildfires. And NASA, when they heard that idea, were immediately enthusiastic and said, "That's perfect. Write that down and send us a proposal." And so at that time, the middle school STEM instructors began to reach out and try to bring in a team of mentors. I had some experience in my undergraduate and PhD programs working with NASA on some remote sensing projects. And so this was an easy project for me to get excited about, but I'd never done anything in terms of building a satellite, and nobody else on the team had either. So it was a challenge for all of us to build up the technical skills that we needed to pull this off. But the students came up with that mission, and that original idea was the requirement that motivated everything else that followed from it. In addition to just engaging the students on the engineering and the ideation of all of this, a big part of the STEM program there at Robertsville and within the Oak Ridge school system that was an important part of this program as well was to have the students learn how to present their ideas to panels of experts, and in this case, considering these experts as their peers. So we wanted them to be able to think and act and present as if they were engineers themselves, getting their ideas in front of their peers, receiving constructive feedback from that peer group, and then responding to it and iterating until we had a design that was going to be satisfactory for the whole team. So this happened many times over the course of the 7-year project. Multiple classes of students going down to Marshall Space Flight Center, going out to Oak Ridge National Lab, teams of researchers coming in as well to the classroom to have presentations and to kind of receive briefings from the students. Really a fantastic thing to witness, and the students got a lot out of that. We hear back from them, and I'm just kind of parroting some of the things now that I hear from the main classroom teachers who they've been using this approach for years, and over the years they hear back from their students that this kind of experience has really made a big difference in their success as they move on to college and then into their professional careers. So another piece of what we were trying to get across to the students is that this is a really hard, complicated problem. It was a hard, complicated problem for any of us, and for the NASA scientists that we were talking to as well. We wanted to impress on the students that this is a very hard problem. It's very complicated, and there isn't any way that any of us were going to get our heads around the whole complexity of this problem all at once. And so a natural way to approach a problem like that is to break it down into smaller pieces. And we use that idea to teach the students about systems of systems. And what I'm showing you here is just a diagram that we came back to a number of times about how those systems were related to each other and how you could think about this big complicated problem as small, hopefully, pieces that were small enough to get a handle on and to make some progress on and gain some understanding of. And if we could have individual students understand any one of these systems sort of based on their interests and their inclinations, we felt that that was a success. And in many cases, there were quite a few students who became experts in a large part of this, and in some cases, the whole thing, they were able to eventually get a working understanding of all of this complexity. I'm going to scroll through an animation of a few pictures here just to show you that this diagram actually mapped directly onto the hardware that we were trying to put together as part of the satellite. See if it will do that for me. Yeah, so here's at the center of this is the flight computer and the software, which was connecting all of the systems together. And so this is the board that held that flight computer, which was part of the motherboard for this system. We also have the imaging system. So the basic requirement for the mission was to have cameras that could take pictures of the Earth, and we have two cameras that you're seeing side by side here. One is, they're essentially identical cameras with slightly different lenses. One of the lenses has the normal kind of IR filter that all of your cell phone cameras have. And the other camera, the other lens does not have that IR filter. And so between that, we could get a combination of visible and near infrared imagery. And that turned out to be very useful for trying to see the forest and the impact of fires on the forest. The power system was an important piece of this as well, and showing in this set of pictures, the battery itself, which is a 10 watt-hour battery, the electronic control system for the battery, and then the solar panels, which were on 5 sides of the satellite. Oops. The radio system was a very complicated piece of this, but in terms of being able to use it and use it successfully, in terms of the hardware, it was a radio that we purchased from a vendor in Kentucky, and that's shown here with its antenna connections. It has UHF and VHF antennas, and an antenna system that was purchased from a company in the Netherlands, which is shown here with two dipole antennas that are curled up inside some really cleverly engineered compartments at the top of the satellite that were deployed after the satellite was in orbit. We had an attitude control and determination system that was based on using sun sensors on the solar panels, as well as a magnetorquer that allowed us to generate magnetic torque that could pull against the Earth's magnetic field or push against it, and hopefully change the attitude of the satellite so that we could keep it pointing down to get good pictures. In terms of the data system, most of our data were stored on an SD card, and there was also some built-in memory that allowed us to store smaller amounts of data for shorter periods of time. And structurally, it was an aluminum frame with a backplane shown here that allowed data transmission up and down the stack of components from the flight computer up to all of the other components. And in the very center of the satellite was a ballast, which was just a big chunk of machined aluminum the students designed and designed the CAD files for that ballast. And that allowed us to stay in orbit for as long as possible by increasing the momentum of the satellite as it was deployed. So those are some of the pieces that we had to put together. In the time that we have, I'm not going to try to explain all of the interconnections there, but we do have all of our software on GitHub, open for the world to see, and we're putting together slowly some user guides for some of the other connectivity of the software, and we have various progress reports to NASA that also document some of that for anybody who's interested in getting into more detail. So one of the really nice parts about this project, as I said, all of the students were who were going through the 6th, 7th, and 8th grade classes. Our objective was to have each one of them have an opportunity or opportunities to have hands-on with the hardware, with the flight hardware, and to do some part of the construction. That depended on what class they were in at the time as the project progressed. But we would meet after school and provide the opportunity for any of the students who were really interested in working hard on this, the chance to come in and really spend as much time with it as they wanted. And quite a few of them did come in and spend their own time after school hours, many hours of time in some cases, working with us and just showing you a few examples of the construction of the satellite, testing of the satellite, and yeah, just working through the process of building it up from its components. In March of 2021, after everything was put together and tested in its final configuration, we took a trip to Houston, to the NanoRacks facility, which is a private group that was providing our launch support. And unfortunately, this was still pandemic restrictions. And so just myself and one of the other mentors, David Andrews, were able to make that trip. Normally for these kinds of projects, the whole team would go and be able to witness that in person, but we had to just Zoom that and let people see it that way. But yeah, so we were there in the NanoRacks clean room and installing RAMSAT into its spring-loaded deployer, which you can see here, which will then go as cargo to the space station. And there's actually one other satellite sharing space in this deployer that was from a university and private consortium in the UK. June 2021, on the 3rd of June at 1:29 in the afternoon, we had our launch. And this was, as I said before, a Falcon 9 flight from Cape Canaveral. And this was a resupply mission to the space station, flying the cargo version of SpaceX's Dragon capsule. That the crewed version is what has been taking astronauts to and from the space station recently. This is the cargo version that doesn't have any crew accommodations, but's full of food and science experiments that go up to the space station. Very cool. We have our own patch that was designed by NASA and sent to us. So everybody was very excited to get that. And we had the launch. We were able to see it briefly before it disappeared into the clouds. And it was a fantastic experience. If you haven't had the chance to do that, they launch now quite regularly from Cape Canaveral, these kinds of flights. And so I highly recommend, if you're interested in that kind of thing, get down there and see one in person. We had a few students who were interviewed on NASA TV as part of the pre-launch festivities. And we had quite a few students. I'll just back up. Oh, actually, I'm sorry, I don't have the full view of all the students. We had about 20 students and their families down there for the launch. So after it gets to the space station, the astronauts take it out of storage eventually, and they load it onto a sliding table that goes into an airlock on the Japanese GEM module of the space station. This is that airlock with its door open and the sliding table, and RAMSAT is inside one of these deployer boxes. The whole thing gets slid into the airlock, and then it's grappled by the Canadian robotic arm. No, I'm sorry, the Japanese robotic arm that's on that module, and then pointed slightly behind and down toward the Earth from the space station, and then released with a spring-loaded release mechanism to shoot the satellites out into their orbit. And there's no power, there's no propulsion on these satellites as part of the safety requirements for launching from the space station. And so all of the momentum that they have all of their orbital velocity comes from the delivery of the payload to the space station. And then there's about a 3 meter per second push out of the spring-loaded launcher that just kind of gets the satellites away from the space station and down a bit in their orbit so they don't run into it. And that was the last time we saw RAMSAT. Pretty remarkable picture. These are photographs taken by the astronauts on the space station as RAMSAT was being deployed. Then we came back to our radio station. After it was 2 weeks between the launch and the deployment, so we were back home already. Once RAMSAT was in orbit, it should have deployed its antennas and began to send its beacon signal right away within the first half hour. And so we scurried back to the classroom and to hear whether we could receive that beacon signal from the ham radio station that had been set up by the local club, and including Jim Bogard, who's back here. Say hi, Jim. Part of the Oak Ridge Amateur Radio Club, and David Andrews was also a critical ham radio operator to get this up and running, as well as Butch Aline and other people from the ham radio community. So on the first couple passes, we did not hear anything, and that could have meant any number of things. Could have meant that the satellite was dead and was never going to be heard from. It could have meant that our receiver wasn't working properly. And just later that day, we got confirmation from a ham operator in Virginia who tracks these kinds of deployments that he had received the signal from RAMSAT. And so there was much rejoicing that we had, RAMSAT was alive and well. And it was just a matter of getting our station at the middle school tuned properly to receive it, which we did. And shortly thereafter, we began receiving the beacon signals from the satellite and made our first command uplinks as well. Very exciting for everybody to be able to have that kind of two-way communication with this thing that we all had our hands on and had been working on for years. So very exciting. And shortly after that, in August, we began to get down our first images, and I can talk a little later about how that works if anybody's interested. But basically just break the image up into a whole bunch of small chunks, hundreds of them, and send those one at a time and receive them at the ground station and stitch them all back together and hope that you're not missing any, and form an image again by piecing all those pieces together. So this was our first view in the visible on the left, in the visible plus near infrared on the right, and we're looking at the southern end of Lake Superior and the Minneapolis area. And we didn't realize how lucky we were at that point to be actually seeing something recognizable, because many of the images that we received looked like this, which is a sun flare. When there's any part of the sun visible in the sensor system, it just swamps out everything else. And so we got about a third of our images have some version of this. Another third are the blackness of space, and about a third ended up being good images of the ground. In September, we got our first really good images with a clear day and a nice downward pointing, nadir pointing viewing geometry. And we're looking here at Atlanta on the left. Well, these are both the same, essentially the same view, the visible image on the left and near infrared image on the right of Atlanta, and north is approximately diagonal in these images from lower left to upper right. So just an example of, I could go on for a long time talking about all the fun things that you can see in these images. They have about a 200-meter spatial resolution, and it's a a 1.2 megabyte pixel, so 1024 by 700 something image, resolution image with JPEG compression. And so you can actually see quite a lot. And this isn't zoomed all the way in. There's more detail that you can see there. You can see individual buildings over in the Atlanta area that are large warehouses, and lots of other fun things: water, mountains, lots of vegetation. I'm going to take just a minute to point out that this is sort of a cleaned up view of what we were able to get after some image processing. The original images all look something like this, with a big glare in the middle of the image. And we were able to, do some image processing to get rid of that glare and then increase the contrast in these images. That turned out to be my fault for having not done a good match between the lens that we were using and the imaging chip that was in our camera. So fortunately, it wasn't a catastrophic problem, something that we could recover from, but it was something that we do differently next time. And I'm going to skip over that in the interest of time. Another cool thing that we've done with this project is we've taken two groups of students in 2 different years, in 2021 and in 2022, to the American Geophysical Union meeting in New Orleans and in Chicago. The last one in 2022 was in Chicago, and the meeting in 2021 was in New Orleans. This is, absent pandemic times, a meeting of 15 to 25,000 scientists of all kinds of geophysical sorts of topics, and a real professional society meeting. And the students submitted an abstract and had a poster there as part of a group of student posters that were connected to NASA in one way or another. Finally, at the end, toward the end of the mission, we got what we were looking for in terms of images over the fire region. So this is a visible plus near infrared view looking down. It's oriented mainly north-south now, with Oak Ridge here, the Cumberland Mountains to the west, the Smoky Mountains to the east, and the fire area. I'm going to zoom in on another image, but this is the crest of the Smokies, and the fires burned in this area. Here's the visible, zoomed in visible version of that image. And this is the fire area. Now this is 2016 to 2022. So there's been almost 6 years for the forest to regrow. And it's very difficult in these images to see the burn scar. You have to really know where you're looking, and then you are able to see it. But if you trace back, say through Google Earth imagery, you can see how over time this burn scar did fill in significantly. And there are still some places where you can see significant burn scars right at the top of the chimneys area. Just a few more images here from 2022, the AGU meeting, and the students had the chance to meet the director of all of NASA's small satellite operations at that meeting. So that was pretty cool. And she knew about the project and was very excited to meet them as well. So that was pretty cool. And I'm going to wrap up with a couple of pictures from what I'm referring to here as an open science consortium that made a huge difference in the success of this mission. So as I mentioned, the very first beacon packets that were received in the ham radio community. And there turned out to be hundreds of stations around the world that were ready and willing to be receiving beacon telemetry packets from our satellite. And then we were providing the decoding information for that. And they were all contributing to an online database, which had a really nice dashboard that we could customize. None of that we really even anticipated being able to connect with, but they were ready to help us out as soon as we were in orbit. And if we did this again, we'd work with them a lot more closely from the design phase. But this is just an example showing you that over the course of the 16 months, there were 46,000, almost 47,000 1-minute beacons received in that community from stations literally all over the world. And this is kind of the leaderboard for who was picking up the most transmissions. And I'll just show you a few more examples of the kinds of information we were sending down that if we had to rely on our own ground station at Robertsville, we'd have gotten 1%, if that, of this amount of data. But because we were tapped into this network of people just donating their time and their equipment to make these receptions and upload them to the database, we were able to get an almost continuous record of, in this case, we're looking at temperature measured at different places inside the core of the satellite and temperature measured on the solar panels. As a result of that, we were incredibly fortunate at the very end of the mission to be able to see the satellite re-entering the atmosphere as recorded by the temperatures on the satellite itself. So this was the core temperature inside the satellite. It sat around 0. It got it sometimes below 0, but it rose up above 45 degrees Celsius in the last received transmission. And this is the temperature on the solar panels, which when they're facing into the depths of space could easily be minus 55 or colder Celsius, or up to 100 degrees Celsius under normal operating conditions, depending on the orientation and how fast it was tumbling. But at the end, the last recorded temperatures were over 180 degrees Celsius. And that was the last time we ever heard from it. So we just were super lucky to get that kind of information from this really great community. And just showing you a picture here of what that information looks like, sort of bit by bit as it comes down and is received at individual stations. There's a waterfall diagram that the ham radio enthusiasts will be familiar with. And then the individual packets, this is what they look like in their hexadecimal representation, and then converted into an ASCII representation. Each packet looked something like this, where each of these numbers is recording some telemetry on the satellite. So I'll end here by just saying that what we've learned in terms of the success of this mission is that by allowing the students to drive the mission and by really pushing this idea of a problem-based learning experience, we were, I think, able to successfully, reach hundreds of students and I believe give them a remarkable experience that hopefully will stay with them through their lives. In terms of the technology, a systems approach to the planning and execution of this mission turned out to be a successful way to do this. Many projects like this don't make it to a successful two-way communication from space. And so we were a combination of lucky and diligent that got us to this point. Collaboration and communication was really important, and that included with amongst ourselves and with this broader community of engineers and scientists and instructors and educators and students around the world. Engaging regularly with our sponsors and our vendors and our flight partners was very important for success, and a real joy for all of us to be able to have these contacts around the country and around the world that we were interacting with pretty regularly. And everybody working together, as I said, none of us knew how to do this at the outset. And so we were truly learning together, and that was a great experience for all of us. And finally, just tapping into this open science consortium magnified the success of this project by 100-fold or more. We got so much more out of it than we could have on our own. And I believe that this global community got a lot out of it too. We heard from a number of them saying that they were really happy with the way that we had engaged, and congratulating us for a successful mission. And I'm going to just leave here a couple of our favorite images. This is a collection of shots from RAMSAT in the, let's see, this is in the visible spectrum, and another collection in the near infrared spectrum. Thanks.
That's just great. Thank you so much, Peter. And Jim, glad you're here also to bask in the glory. So I guess all of us have thoughts and questions. It looks like you really used that data from SatNOGs well. And I saw the little line there. It looks like they did not Doppler shift it before they presented it.
No, they did. In this case, this was the very last transmission that was received. And so
So that's why it would be.
yeah, in order to do the right Doppler shift, they needed to have that typically came from the Space Force wing that's dedicated to doing those radar detections of everything that's in orbit. And in this case, it was changing so fast that their two-line elements were out of date before they could be used. And this observer was one of the most skilled observers in the network, actually runs the network, and they come up with their own two-line elements based on three-line elements. Now I can't remember. Thank you. Two-line elements based on the observations that they were making, which were more accurate than the observations that the Space Force was making, and was able to update it fast enough to get this. But yeah, normally they'd have been lined up with the Doppler shift.
No, that's a remarkable thing that they've done together. A bunch of amateurs, a bunch of people that got together and built the SatNOGs array. So many people collaborating. We had a little group here trying to follow along. We built, we put together a ground station, and then we hooked up with SatNOGs, and it was interesting. We did check it out partially, but we encountered that SatNOGs does not want us to test our system with any sort of local transmitter to see if it's functioning. And actually we sort of did, but it was kind of a kludge. Did you encounter that? Did you try to test your system before you launched?
We tested it locally just on our own radio, but at that time we were not connected to SatNOGs. And eventually David Andrews I didn't even mention this, but he had a second ground station at his house that was also key to our success, because lots of times we couldn't get to the school when there was an overpass, but he could get out of bed at 2 a.m. and go downstairs to his luxuriously appointed cave and collect data. And he was also feeding data into the network. He was a recognized station, a SatNOG station eventually.
Yeah, he's an energetic guy. I got together a little group. We went over to see him, and yeah, he's not uncomfortable at 2 a.m. sitting downstairs.
No, he wasn't. He was happy to do it.
I'm just going to pass my phone around if anybody wants to ask questions or have comments.
Sorry, John, I missed that. Did you say that again?
Yeah, I'm curious as to the altitude of the orbiting satellite.
Thanks. Yeah, it was at a 450 kilometer. Oh, let's see. I've got some.
450 kilometer.
Kilometers, and then it came down to the last recorded altitude was, I think, 180 kilometers. It was a steady decline over time, and then a rapid decline over the last few weeks.
So you're right. You're right up there in the F layer thereabouts, in the ionosphere. And I'm wondering if you made any measurements about. Well, I guess it was just an optical program that you had going, but it would have been interesting to study the plasma characteristics of the ionosphere altitude.
Yeah, the only science instruments were the temperature sensors, the solar, the sun sensors, and well, yeah, we had magnetometer and measuring the magnetic field. And I didn't show you this, but that was pretty interesting. We could see very clearly the rotation of the satellite based on both the sun sensors and the magnetometer. But yeah, that was the only other besides the.
So if you have your magnetometer data handy, it would be easy to go to an FFT on it, and your rotation speed of the satellite with the tumbling speed would pop right out of that.
Yep. Yeah, and in fact, it had an algorithm that we had built into it on board to be able to assess that magnetic field information together with the sun sensors and try to assess its own orientation. It was easy to get the rate of rotation, but knowing exactly which direction it was pointing at a particular time was very difficult. And in the end, not successful. We were able to detumble it with simple algorithms that were kind of built into the magnetorquer, but we were not able to intentionally point it in any meaningful way. We decided we would probably need something like a much higher resolution sun sensor or a star tracker, ideally, to do that correctly, and that doubles and triples the cost of hardware.
Fascinating project.
Was there anything to see when it came down to the atmosphere?
Well, those images, the best images that we got of the fire scar area were October 5th, and it re-entered on October 11th.
Wow.
So we were incredibly lucky to be able to get it, a nice clear day with a nadir pointing view over the target area, just 6 days before it completely burnt up. And the fact that it had already lost a tremendous amount of altitude by then meant that our resolution was a lot better than it would have been otherwise. Yeah, so we got very lucky on that count.
What I was curious about was when something like that small comes down, is it like a shooting star?
We think that somebody in the right place at the right time could have seen it.
Oh, what a great ending to the program. Got a picture of it.
Yeah, and in fact, one of the students, there's a meteorite database of observations that people send in from around the world, and one of the students tried to match up our demise with those observations, and there was nothing. But it was literally over the middle of the Indian Ocean when it was coming down, so very unlikely that anybody saw it.
I have a quick question. Did any of the students involved in the project change their career goals as a result of this?
I'm not sure if it's hard to know change, but several of the students who have recently graduated and from high school and gone on to college are in aerospace engineering or some other kind of engineering, and they have told us that the experience was formative for them in terms of selecting that pathway. And it's hard to know, however, I wouldn't expect that a lot of the students would end up in that particular, an aerospace kind of pathway, but the experiences that they got hopefully would be useful for them in any number of pursuits. So hope so.
If nothing else, it was a lot of fun for all of them, I'm sure.
Yes, yes.
What instruments did you think of and say, wow, I wish we'd put that on board?
What instruments?
Yeah, what other things?
Let's see. Jim, can you think of anything? Well, a higher resolution sun sensor, so that we could really know which direction the sun was. What we had was free, but pretty low resolution. Free in that the provider who sold us the panels installed the sun sensors, a coarse resolution sun sensor, because they were testing it, and gave it to us for free. Let's see, what else?
What do they have to say about the sun sensor not performing all that well?
It performed to spec. It just wasn't enough. It wasn't good enough to be able to really tell. And it had some issues with the calibration of it was not really great, and the calibration of the magnetometers was also difficult because we didn't have a really good way to test the fully built thing and tune the magnetometers against the background of all these other electronics. The other thing that on the ground that I wish we had is an air bearing setup that would allow us to test the magnetorquer. So we tried several different ways to have low friction environments where we could set up the magnetorquer and try to get it to move against the Earth's magnetic field.
Hang it from a string.
Yeah, we hung it from a string, and in the end, the forces generated are very, very, very small. The lever arm is the equivalent of a grain of sand at 10 centimeters. So there's not a lot of force, but routinely groups that have access to a good air bearing, hemispherical air bearing, can get these things to work. And we just didn't have access to it. And I searched around at the lab and nobody had one. And we'd want to do that better.
I've got a 4-inch ferrite core, I guess, with a couple thousand turns on it.
Yeah, it was, I can't remember the exact specs of it, but there were 2 ferrite coils, and then a third coil was an air coil, just in the Z direction around the board, essentially. The other thing that would have really helped in terms of the attitude control would be reaction wheels. And we could have done that. They're expensive, but we had space. We could have swapped out the ballast for the reaction wheels, and the weight difference would have been very similar. Or we could have moved up to a 3U. This was a 20 centimeter by 10 by 10 form factor, and we could have moved up to a 30 centimeter by 10 by 10 and still been within our launch specifications. But we didn't know at the beginning that we would need that, and it would have not quite doubled, but added another $20,000 to the cost to have reaction wheels set up. But that's a much more effective way to aim it. Hey, David Andrews is here. Hello, David.
Hi, Peter. Just want to add 2 comments. I remember that we talked about, and it was after the fact, but we talked about it would have been better to have a higher resolution camera for the images. And the other was, we talked about having a higher bandwidth downlink. That was one of our weak links. So possibly a 2.3 gig downlink, which would have added more hardware both on the spacecraft and on the ground, but would have greatly increased our abilities to download images.
Yeah, we were working 9600 baud for all of these image transmissions. All of that said, all of those would be nice to have had. Our design philosophy was to make it as simple as possible and still accomplish the mission. And I'd say we did that. We couldn't have left much out and still had the success that we had. And we did in the end get images of the fire scar area. So it wasn't ideal, but it was our definition of success was met.
Right.
Seriously. Get in there.
Hey, I see Ian Gothert. Ian, anything to add on?
I would say that the TNC, the more expensive TNC that would support a binary transmission would have saved a lot of time in transmission. But again, I think I would echo back what Peter said. We took that opportunity to teach the kids about binary and hexadecimal and conversion to ASCII, and it was really just a great learning opportunity for the students, as it is.
It's a good time to ask you guys if you're pushing the limits. I'm surprised that NASA likes the idea of you having cameras in orbit, and that they would let you go to the higher frequencies without questioning. Is it still within the ham band limits?
Yes. So the two separate issues there. One is the camera resolution. So we had to get a remote sensing license from NOAA, and of all of the licensing, that was the most the most difficult and the most required the most interaction with the licensor and the most information. They wanted to know absolutely everything about what we were doing and what the final resolution would be and how much control we'd have over the pointing. And in the end, they said, okay, you're fine. But if you end up having pictures, it was kind of in their purview to review everything that we got and to restrict it if needed. And then the ham license was also not simple to organize. The NanoRacks launch service provider was very helpful in getting us connected with the ham licensing documentation that we needed with the FCC. And then, is that right? FCC? Yeah. And then we coordinated our frequencies with the IARU, and that was not absolutely necessary, but it put us in the good graces of this whole SatNogs community. I've learned since that they're not very happy to work with teams that have not done this amateur coordination. So, yeah. Yeah, Jim, you want to start off? Anything you want to add to hints from the? I'm going to scoot up here a little bit more and you can be seen.
I was mostly an observer and documenter. So, but I will note that there has been talk of doing this again at the high school level. I don't know if there are any solid plans to, but it's certainly been discussed.
I would have to say that the biggest requirement to do this is somebody like Peter to be able to coalesce around and to have a group of people who are crazy enough to spend their every waking hour on this. It's a tremendous labor of love to get this done, and you can't even think about doing something like this without having a Dr. Thornton in the middle of it. You have the abilities to not only get the most out of people, but also to keep the kids really encouraged. There was those couple of times that it was really getting worrisome if we were going to pull this off, and he never lost faith, never lost hope, and kept everybody focused on the mission. It also helps to have plenty of sponsors with deep pockets and a school system that had an unwavering faith and support in doing this. I think it's noteworthy that when you consider when we started this project, I believe there was 11 or 12 satellites that were supposed to go up on that mission. This is the resupply patch, and each of those stars represents one of the satellites that was supposed to go up on the resupply mission. And when the time came for that launch, the junior high kids were the only ones that pulled it off. Everybody else missed for one reason or another. And we were up against major universities with practically unlimited budgets. And I hate to gloat, they couldn't do it, but Peter and his team pulled it off. So you can't discount the leadership.
Hey, Ian, ask you to say something too, and I just let everybody know the programming for the ground station, which was taking sort of our raw data stream and turning it into something useful on the ground side, as well as the ability to deconstruct and reconstruct the images, was all thanks to Ian Gothert, and developed that from the ground up, and also the whole command and control interface for interfacing to the ground station radios to be able to send commands and receive the information back was all Ian's doing. So Ian, want to add anything?
Oh, I don't think so. Yeah, I mean, it was a great project. It was a lot of fun. I think we all learned a lot, and we're all looking forward to maybe doing it again in the future.
Did you say that there were like 23 single failure points that would have been disaster for the mission? Or was it more?
Well, that's an understatement.
Yeah, there's a lot more than that, I'd say. But what we, at the very beginning, and David Fields, you might remember this, we laid out a list of, I can't remember how we phrased it, but it was our success, our gradated versions of mission success. And the first level success was just doing our due diligence, making sure that we had done everything that we could to test, to build and test the system, and delivered it on time for a launch to NASA. And then it was kind of out of our hands. That was first level success. And then we had 17 or 18 different levels after that, which were, have it deploy its antennas, have it send its first beacon, be able to have two-way communications, and be able to change its orientation with the control system, and be able to command it to take pictures and then be able to send pictures back. And finally, I think we even said to be able to track its demise, or see some evidence of its deterioration as the orbit decayed. And we ticked every box. Not, sort of a pencil tick on a couple boxes, but it was a tick.
Maybe that's where I got to 23.
Yeah, I think that's
Yeah.
what you're thinking.
It was very successful. I was just amazed that, most of these amateur built CubeSats do not work. They don't even come online. And very few of them have this success. Maybe none.
Peter mentioned that at first we could not hear RAMSAT, and we were wondering if it were alive until we got the feedback from the SatNog station.
Yeah.
And it turned out we had aligned the antenna, I guess it was probably months before, and a roofing crew had gone up there, and they moved the antenna and then set it back to where they thought it was supposed to be. But it was not aligned.
This
And so,
was at the school site.
as at the school, yeah. So once we aligned the antenna and then we were actually tracking the satellite.
That was not one of the checkboxes in the list.
That was
Just
not,
check,
no.
antenna. See what the roofing crew is talking.
We also found out that the HVAC system at the school was sending RF that was within it sounded like the squawks that you hear in one of these packet transmissions.
it actually had detectable like ASCII text in these packets that would come across from the HVAC. So it was an AX25 packet, which is what we were using. And it was showing up as something that you could read. And we're like, where is that coming from?
Just got a bug in it. So it translates to a Chinese balloon.
Yeah.
Maybe.
We had a long series of trial and mostly error or lack of success to have solid two-way communication in the classroom. And that was which I was the most concerned about our ability to pull this off, is that I knew if we weren't able to have the two-way communication happening within the confines of the classroom, there was zero chance that we were going to be able to do this from space. And we were having a hard time getting in touch with the radio manufacturer. But in the end, we did get some really nice guidance from them, and were able to set the deviations on the radio and on the receiver on the TNC to get it within the right, and a lot of other trial and error kinds of successes that David Andrews was particularly key to sorting out, that finally got us very solid, reproducible communications on the ground. And once we had that, that was kind of the last piece. I said, okay, we're pretty much good to go. Everything is working as designed.
Well, in fact, that communications testing is what uncovered a problem with the chip on the.
Oh, yeah.
Yeah, because I think that Peter mentioned that we had to unbuild and rebuild it. And that's because there was a short in a processing chip on the motherboard, yeah. And we probably not have found it, except that we were trying to do communications testing and we weren't having any results.
Yeah.
And yeah.
That's a very complex.
What was your communication frequencies, ballpark?
So golly, uplink was 2 meters and downlink was UHF.
Uplink was 145.9, downlink was 435.6, I believe.
That's megahertz?
Yes,
Okay, then you're fine.
Doppler adjusted, so UHF down, VHF up.
But eventually we were driving it around in a car to the most distant places in Oak Ridge that we could still have line of sight to the radio station on the to the antenna on the roof of the school, and getting consistent connection across miles. So that was as much testing as we could do on the ground. Thank you.
We have in our meetings, and sometimes have an AstroCheck. It's other times, more often than not, photography. So this is relying on Ted Barnes, who was very active at our Tau Stargaze 2 nights ago. And who actually found a supernova 2 days after it started shining.
This is Ted Barnes. I hope you're hearing me. I have a series of images that I do once a month at the Orion meetings called the Big Kitty series. This is my very own kitty cat named Franny. And this is the 5th of these monthly series. So that explains the terminology. And so it's meant to get everybody's attention that Big Kitty is watching you. So you should be paying careful and close attention. All right, so this is Tau images, not from this month. We had a slightly early session this month, which was just the 17th of June. This will be almost all images from a month ago. I've got one from this most recent session that I'll throw in for reasons that will become obvious, I hope. Okay, so here we go. These are from Tau a month ago, and what I do is I show up with nominal targets of things that I'd like to have pictures of. If everything works perfectly, if I get the telescope aligned quickly, if I've got lots of time, and if there's no trouble with the weather. That, of course, never happens. So this was my list of things I'd nominally like to get images of on the 21st of May last month. The first one was the moon. I usually don't bother with the moon. It's too big and bright and arrogant, and so to hell with it. But in this case, it was a crescent moon low in the west, and it was only at 22 degrees altitude at 9 p.m. and would be setting fairly quickly. So and David asked me in particular if I would mind trying to get some pictures of the crescent moon. So I have one of those. For galaxies, I had a list of a 5-year-old article on amateur astronomy about good things to look at in May. M101, a beautiful spiral galaxy in Ursa Major, was one of them. So that was a warm-up. You do something simple first. Then I had two somewhat more obscure spirals. One was called a grand design spiral. I just love that term, so I was going to go for that rather fainter one, NGC 3310, and then something called the Lost Galaxy, barred spiral in Virgo. I thought with a name like that, I've got to try for it. The really fun thing for me was I was going to take my first ever image of a supernova. I'm the editor for the monthly Trapezium magazine for Orion now, and I added a little supernova, hello David, little supernova section. And so I picked out two of them and I was ready to go after them. One was a type 2 in Virgo, magnitude 14.7. That was the brightest currently available. And of course, as a physicist, I'm interested in core collapse supernova, a little bit more than the accretion white dwarf blow up ones, the type 1As. So anyway, there's one of each, a fairly bright type 2 and a somewhat less bright type 1A in Coma Berenice. All right, so those were on my list, and that's why I was excited. This was going to be my first ever image of a supernova, if things went well. Next, I track down dwarf planets. These sort of come in about 17th magnitude. If you know astronomy, Pluto is 14th magnitude, and each additional magnitude gets you 2.5 times fainter, roughly. So 17th magnitude is getting hard. Anything below that is really hard. So I was going to try to catch one of the TNOs, one of the trans-Neptunian objects that I'd never seen, which is number 20,000 Varuna. And then two globular clusters, I was going to go after two very distant ones. One, 2419, has been called the Intergalactic Wanderer, because when it was first discovered, it wasn't clear if it was ours or just some globular wandering between the galaxies. Now it's known to be ours, but it's still very distant. And the last one was Palomar 3 and the constellation Sextans. That's also very distant, about the same distance. And it's where I'd previously been able to pick out the very faintest stars I've ever seen with my setup, which are 21st magnitude. I've never been able to quite equal 21st. It was a lucky night or something. Okay, so here we go. That's my nominal shopping list. Here's what I actually got to. As usual, not very much. The problem was when driving to the dark sky site near Kingston, I noticed the skies were really hazy. Mountains were kind of gray and faded out. It looked like Los Angeles. And there was so much haze in the sky, even though the clear sky chart said this is going to be a great night, that you couldn't even see Polaris until about 10 p.m. So I couldn't even align the telescope and figure out which way it was pointing. I did have the moon as a possibility, though. There was a crescent low in the west. And so after waiting and waiting and waiting for Polaris, I finally gave up on it. And just with hand controller, went down to catch the moon before it vanished. It was only at 14 degrees altitude. I caught it. Next, for galaxies, I went to M101. I tried to take a fairly quick picture, a couple of minutes of exposure time on M101. I couldn't even see the spiral arms. There was so much haze in the sky, but I did discover there was kind of a surprise. The next two galaxies, 3310 was very disappointing. It wasn't really a good sky. And the Lost Galaxy, I ran out of time. For supernovas, I decided to go after the type 1A in Coma Berenice, but it had faded. It turned out it was about 5 times fainter than the previous published observations of it. It was down to 17th magnitude, but I did manage to get that one. So you'll see what I thought at the time was my first ever picture of a supernova. And then the other targets were just by the time I had a chance of getting them, they were too low in altitude. All right, so here we go. Here's the first thing. There's the crescent moon at Tau. You have to play around with exposures to see something that's going to look nice. You never know for sure. And I've got some little icon that's blocking some of the stuff I wanted to see. That's just the date, I guess, 21 May. So anyway, that's a 1 millisecond exposure at a fairly high camera gain. This is just the raw image before I did any post-processing. And you can see it's kind of charming in its own way. You can just see some craters along the limb of the moon. If you ran for longer exposure, like 2, 4, 8 milliseconds, it started being overexposed along the limb, and then the interior region sort of turned into a donut illumination that wasn't nearly so attractive. So this was my favorite, and I used this one to post-process. And there's the post-process version, where I've stretched the contrast a little bit. It turned out that was, since it was 943, that was only an altitude of 14 degrees. And staring at moon charts and twisting this around both ways, I was able to identify some of the craters. This is on the lower right-hand side of the moon. I don't know much about the moon, actually, so I don't know the features, but there are 3 craters that I could identify fairly easily. They're Adams, Legendre, and Phillips. And I twisted it around, that image around, so that's roughly the orientation that it had when seen from Tau. Okay, so that was kind of a success, nice moon crescent. Now, next I had, remember, a quick warm-up attempt at getting an image of M101 that I was unhappy with. So there it is. It's called the Pinwheel Galaxy in Ursa Major. When I actually looked at the image, I mean, you're kind of looking at things with red plastic over them, and you haven't been able to stretch the exposure. So it's kind of hard to tell if you're getting a really interesting image or not. And with that 2-minute exposure you're looking at there, very short one, I couldn't even see any spiral arms. So I thought, to hell with this, I'm wasting my time. So anyway, I got a surprisingly good, after post-processing, image of M101, and I'll come back to that in a minute. But that's, you know, like I said, that's just 2 minutes, very short at a high camera gain, but I was starting to see the time going by quickly. It was already 10:30 p.m. and I wanted to get a picture of a supernova, damn it. So I just said, goodbye, M101, let's go to this faint little supernova that's in my data that I got from online sources. So the supernova, you can see the galaxy first. It's a faint little spiral galaxy called the NGC 4611, quite distant, 90 megaparsecs, so 300 million light years roughly. Magnitude 14.7. That's a 16-minute exposure. Now that number salad there, third from the bottom, says it's a stack of 240 individual exposures, each 4 seconds long. Those are called frames. With a gain of 540, which is a pretty high gain. Now, the software in the camera, which is called SharpCap, it's just brilliant software. It takes each one of those individual 4-second frames and translates and rotates it until it's got the best possible alignment with the running stack. You know, everything fits on top of everything else. And so it just stacks them up as it's running. So you see an image gradually building up with higher and higher contrast. And so that's the result of a 16-minute effort to get this thing. There's the galaxy, obviously. Nice orange hue to it. Here's the supernova. So that, I thought, was my first ever image of a supernova. They have their own jargon. So it's 2023, obviously the year, and then DTC, 3-letter code, in the constellation Coma Berenice. The galaxy is about 15th magnitude. The supernova, as I think I said, turned out to be fainter than promised. This is only 17th magnitude. Now, one of the ways you can tell that is by comparing with the field stars. I looked up all their magnitudes. So there they are. Every dot you can see, there's a field star. And for example, I'm not sure if I can get an arrow on here, but
yeah, you can just.
Oh, okay. So anyway, there's the supernova. Now, if you look to the left, You can see that star is magnitude 17.8, literally somewhat fainter than that supernova. But over here is a 17.1, and that's maybe a little fainter than the supernova, maybe not. There's another one over here that's 16.3, which is clearly brighter. So my ballpark guess is that we're a little bit above 17th magnitude. So this guy has faded considerably from the previous one's observation that said it was at about 15.9. Okay, so I've taken my first picture of a supernova. I thought, oh, for how awful the skies were, you can maybe just barely make out that there's a 19.6 magnitude star there. You see a little faint red glitch. That's 20th magnitude. 19.5 to 20.5 is legally 20th magnitude. So that's the faintest sky. So it wasn't such a bad sky in that direction. This is fairly high up in altitude and pointing away from Kingston, Tennessee. So escaping a lot of the junk. Now let's go back to M101. I thought I had taken my first ever picture of a supernova with that faint little guy. I was wrong. There's a supernova in this picture. It's right there. And M101, it had been seen 2 days before this dark sky trip. It was reported on the 19th of May. This is the 21st of May. Reported at magnitude 14.9. Here it's about 11.8. It's the first supernova in M101 in 12 years. And I didn't know it had gone off. I just happened to get it in this picture of, let's try M101 as a practice image. So that's my actual first ever picture of a supernova. That was half an hour before I went over to the faint little galaxy. And so talk about serendipity. That was just great. Now, for I think my last image, somewhere near the last, is the thing as it looks now. Yeah. So here's M101 with a proper amount of time spent on it. That's a 30-minute total exposure from 2 nights ago, 11:16 to 11:47 p.m. And same orientation, so the supernova is right there. You can see if I can back up and compare it with the previous image, you can see it's faded considerably relative to that. It's probably not a star, it's probably an open cluster next to it. So there we are. All right, so that was a real thrill. I'd thought TAL wasn't really going to work out very well that night because the sky was so gray and everything, but I got my first 2 pictures of supernovas there. So that was fun. You never know what you're going to get, but you always get something. Okay, that's the end. Big Kitty was not watching you. We just got her a cat bed and she spends a lot of time curled up in it. All right, that's the end. Thank you.
Okay. Okay, folks. This is important. Peter, you step over, you'll be anointed, presented.
Oh,
Hang on,
With-
I need to get a picture.
An Orion Cup.
oh my goodness.
3.
All right.
Another.
3, 2, 1.
Okay.
Thank you. Thanks a lot.
And you already have the one before, right? You talked with us before. Did you get a cup?
No,
Oh,
that's my
yeah.
first Orion Cup. I'm
Okay.
gonna treasure it.
Maybe that's what